Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're doing problem number 4.40 from Elementary Principles of Chemical Processes, 3rd edition. The problem statement says, ammonia is burned to form nitric oxide in the following reaction, and then they get the reaction right here. Part A, calculate the ratio, pound moles of oxygen react per pound moles of nitric oxide formed. Okay. Part A, basically you just get these from the stoichiometric ratios here. Oxygen reacted per nitric oxide formed. There you go. I think maybe they were trying to throw you off on the pound moles thing because people aren't familiar with using pound moles normally. From chemistry, you just kind of use gram moles. Basically, you use them interchangeably. Like they're the same thing. Only for every 1 pound mole, you have to convert pound moles into pounds or whatever. Like if you're working in pound moles and you want to know how many, if you're converting that into a molar mass, so to say, the molar mass of nitric oxide or ammonia or whatever, if you're converting this, then the mass in the molar mass would be in pounds. So if you have 1 pound mole, then you have a certain number of pounds of whatever the material is. So for nitric oxide, it's 17.31. 17.31. Okay. So yeah, you don't really have to know this in order to do this part. You're just looking at the stoichiometries. So regardless of, whether it's pound moles, kilomoles, gram moles, whatever, it doesn't matter. As long as these units match each other, they're going to cancel out. So anyway, hopefully that's helpful for you guys. Let's move on to part B. If ammonia is fed to a continuous reactor at a rate of 100 kilomoles of ammonia per hour, what oxygen feed rate in kilomoles per hour would correspond to 40% excess oxygen? Okay, so you got your reactor here, you have a certain feed rate here, and then a feed rate here. We don't know what the feed rate is, so we have to calculate what that is. So we'll use our stoichiometry from this equation in order to figure that out. So we want to know what the feed rate is. So using the ammonia feed rate, we can say, okay, for every 4 moles of for every 4 moles of ammonia, there are going to be 5 moles of oxygen if they were perfectly mixed at stoichiometric ratios. But we know that the oxygen is in 40% excess, so 1.4 excess. So then the oxygen ratio is 175 kilomoles of oxygen per hour. Okay, so what that comes from is basically, I'd say, X number of moles. If I'm including excess, then I would say X number of moles plus X times 0.4, right? But then I just factor out that X, and then that equals X times 1.4. So if you're doing 40%, that's where that 1.4 comes from. Okay. Okay. Part C. If 50 kilogram of ammonia and 100 kilograms of oxygen are fed to a batch reactor, determine the limiting reactant, the percentage by which the other reactant is in excess, and the extent of reaction in moles, and mass of nitric oxide produced in kilograms if the reaction proceeds to completion. So there's quite a few things in this one. Basically, this is how you would set up what that would look like in like a flow diagram. So stream 1 has the ammonia in it, stream 2 has the oxygen in it. But we don't know which one's in excess because it's in mass, and we need to convert this into moles if we want to work in stoichiometry and things like that, and reactions. So whenever you have a reaction, you have to work in moles, you can't work in mass. So we have to convert everything into moles first, okay? So we'll convert these two flow rates into moles. That's the first thing we do. Okay, and now we can determine if it's in its stoichiometric ratio, and if it's not, we can determine which one is the limiting reactant. The limiting reactant is going to be the one that is making it less than the stoichiometric ratio, or more than the stoichiometric. We'll see. I'll explain it right here. Okay, so this is our ratio, N2 to N1. So this is our oxygen on the top and our ammonia on the bottom. Okay, this is our stoichiometric ratio. If we have oxygen on the top, we have 5 moles, and if we have ammonia on the bottom, we have 4 moles. Okay, this ratio is 1.25. We notice that our ratio from mixing these two things is 1.06. Okay, so our ratio is smaller. This number is smaller than this number. So what does that mean? It means that the bottom number here is bigger in relationship to the bottom number here. So if N1 is bigger in this ratio than it is in this ratio, then our N1 is stoichiometrically larger than this N1, which means this N1 is in excess. Okay, I pause to help you think through. It also helps me think through. Okay, stoichiometric ratio is larger than added ratio, therefore, that's what the 3 dots are, therefore ammonia is in excess. Okay, so in this part I'm saying, okay, if ammonia is in excess, we need to answer, okay, how much in excess is it? Okay, so starting with the limiting reagent, which we now know is oxygen. Oxygen is the limiting reagent. We would calculate how much ammonia does that correspond to. So how much ammonia is going to react with all this oxygen? Well, we say, okay, divide that by 5 and multiply it by 4, because for every 5 oxygens, we get 4 ammonias. Okay, so that grabs 2.5 kilomoles of ammonia is consumed in this reaction. But there's stuff left over, right? Because we have 2.9, right? So how much in excess is it? Well, 2.9 minus 2.5 is 0.436, okay? So we have that much in excess, okay? Now we're going to answer the question. The percentage by which the other reactant is in excess. Okay, so we know oxygen is the limiting reactant if this is in excess, and we know that it's in excess by, okay, this is how much is consumed, this is how much is extra in excess, so we have 17.4% excess, okay? Then we need to calculate the extent of reaction. Okay, I haven't covered the extent of reaction yet, and so I'm just going to cover that right now. The extent of reaction. This is the formula for the extent, what, glitch? Okay, this is the formula for the extent of reaction. Okay, I'll define each of these terms. Ni is the equilibrium amount. It's not how much you started with, it's how much you end up with. After everything's said and done, the reaction's either gone to completion or it's reached equilibrium. This is how much you ended up with, and I stands for any component. Okay, so I is just changeable, interchangeable with any of these components. So this one, this one, this one, this one, any of the components in the reaction. Okay, that's what Ni is. Ni0 is how much did you feed into the reaction? How much did you start with in the reaction? And that could be either a It could be either a reactant or a product. Maybe you start with a little bit of product in your stream because you have a recycle stream or something like that. So it can be either a reactant or a product. You can start with a certain amount of either one. It's how much you started with, okay, before the reaction occurs. Okay, that's what the little 0 stands for. Okay, VI. This is actually nu I. Nu I is the Greek letter nu. I stands for basically just these stoichiometric numbers. So 4 would be nu ammonia, nu oxygen, nu nitric oxide, nu water. It would be these numbers right here, the stoichiometric number. Okay, that's what nu is. There you go. Here's the other deal. If you're dealing with a reactant, then the stoichiometric number is negative. If it's a product, the stoichiometric number is positive. Okay? So you grab the number, whatever the number is, 4, 5, 1, 2, whatever. You grab that number, and if you got it on the product side, then it's positive. If you got it on the reactant side, it is negative. Okay? This number, or this letter, this symbol, is like epsilon. I don't know what it's called. I can't remember what it's called. I think it's an epsilon. Could be totally wrong. I'm not super familiar with all my Greek stuff. But it's a Greek letter, and we use it to represent the extent of reaction. That's as much as I know about it. All right. Now that we've got our general function and we know what all these terms are, we just plug in each one of these things. Okay? Stream 3 of ammonia, stream 1 of ammonia, and then our stoichiometric number. Remember, it's negative because it's a reactant. And then we don't know what our extent of reaction is. That's what we're solving for. Okay? We started with this amount of ammonia. We ended with this amount of ammonia. Then we solve for epsilon. This is epsilon in kilomoles because we solved in kilomoles. Okay? And then we converted into moles because it asked for moles. Yes, the extent of reaction does have units. Okay? So pay attention to that. Extent of reaction does have units. Okay. Now we're trying to figure out, we can use the extent of reaction on any one of our things now. So now that we know what it is for ammonia, we can use extent of reaction for any of the other products that we have, products, reactant, whatever. So now we just change our symbols over from ammonia over to nitric oxide, and we can solve. So we don't start with any nitric oxide, so that's 0. And then we can figure out, okay, we produced 2.5 kilomoles of nitric oxide. Well, that's in kilomoles. They asked for kilograms, so let's use the molar mass in order to convert that, and bingo. That's how you do it. All right. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.